quickly, some reaction can take long time to complete. Okay, so this chapter is about speed rate of chemical reactions. Okay, there is one more question in boards, and so the first question which we is being asked in this chapter is, what is chemical kinetics? So it is a branch of chemistry which deals with the study of rate of chemical reactions. Okay, and it also not only the rate of chemical reaction, it also tells us about the effect of temperature, that how the rate is going to increase with the increase in temperature, what will be the effect of concentration of the reactants. Okay, pressure of the reactant, what is the mechanism of the reaction? Mechanism means how the reaction is being taken place, which bonds are being broken first and which bonds are breaking afterwards. Okay, which is the fast step which is within the reaction only. It could be a multi-step, whether it is a multi-step or single step. So all such things come under chemical kinetics. Okay, so this is the basic definition. And next is there are three types of reaction. If I try to segregate them in terms of speed, there are reactions which are instantaneous reaction. There are reactions which proceed with a moderate rate, means neither fast nor slow. And there are reactions which can take very, very long time to complete, and they are very, very slow reactions. And instantaneous reactions are example precipitation reactions. PPT reaction means precipitation reactions. Okay, PPT reaction, we have seen that when you put NaCl and when you put silver nitrate, when you mix them together, immediately you see a white, curdy white precipitate being formed of AgCl and NaNO3. NaNO3 is soluble, so that will not form the precipitate. Okay, AgCl white precipitate will. Okay, so why this reaction? Just you need to mix it. The moment you mix it, you get the precipitate instantly, instant reaction. It doesn't take any time. It's not that it is going to take some minutes or some hours, half an hour or 1 hour to get completed. Instant. It happens because if you look at the nature of the reactants, you will be able to understand. NaCl, you know, it is made up of
Na plus and Cl minus.
exactly Na plus and Cl minus. Got it? So both, and it dissociate completely. Similarly, Ag plus is made up of Ag plus and
NO3 minus.
NO3 minus silver nitrate. Yes, exactly. So now what happens? And in the water they remain separated. So you don't have to break any bond. That's why it doesn't take any time. And the moment you mix them together, Ag plus and Cl minus combine with each other, and they form a precipitate, white precipitate. And this is a very, very famous reaction in whole of class 12th and 11th chemistry. They are going to ask which compound is going to give you precipitate of AgCl or precipitate with AgNO3. That is the one which can, in which the Cl can come out easily, and it is going to, because no bonds are being broken in the reaction. So that's why this reaction is instantaneous and it can happen very quickly. Okay, so such reaction can complete in 10 to the power minus 3 seconds, just fraction of a second. So there is no point in studying their rates. Okay, because they are instantaneous reaction. There are a lot of other instantaneous reaction also, like explosions. They can occur instantly. Okay, so, and there are on the extreme end, opposite end, you have reactions which are very, 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 very slow. They may take many years to complete. Okay, for example, formation of minerals, formation of oil in the earth's crust. So that reaction may take very long time to complete. Formation of diamond under the pressure. So such reactions are also rusting. That also takes a long time. So such reaction also there is no point in study. Okay. So most of the reaction in the lab which we are dealing with are the reactions with moderate rate of reaction. I mean, they are neither too fast nor too slow. Such reactions will be of our interest in this chapter. We will be studying uh, uh, reactions which can complete in a some limited time period, which is neither too small nor too long. So these reactions are the reactions which occur with moderate rate, and they will be studied in this chapter. Okay. Now the next thing is how to check the speed of the reaction. Suppose if we are sitting in a car, how we check whether with what thing gives us idea whether it is moving fast or moving slow? How we know? There is yeah. Tell me if you want.
When you, with respect to a reference particle, or
Yeah, exactly. So you in the car, suppose if we are traveling, we have to look outside. If you look outside, we can see how quickly the moves are. Things are moving back in the opposite direction. So we can imagine, oh, the car is moving very fast. Okay, we are driving very fast, and there is a speedometer also. Okay, so that's the way. And we try to make out that how much distance is being covered and how much time that actually tells us about the speed. Similarly, in chemical reactions, you study the rate by studying the rate of change of concentration of any reactant or product. To know the speed of car, you need to measure how much distance is traveled in how much time. To know the speed of chemical reaction, you need to know the change in concentration of either reactant or product per unit time. Okay. So in experiment, you take the samples, you measure the concentration, initial concentration after 5 minutes, after 10 minutes, after 20 minutes, and with that, and the concentration of the reactant, suppose if you are checking, the reactant concentration will be decreasing. So you measure the concentration. Okay, this is the concentration. And this is the time. As the time proceeds, the concentration of reactant decreases, it comes down. Suppose it is 10 moles per liter, then it becomes 5 mole per liter. Okay, in let's say in 1 minute, 2 minutes, 3 minutes, like that. So you try to make out what is the change in concentration per unit time. You divide by change in concentration by the time taken for that change. Okay, clear?
yeah.
So that gives us the rate of the reaction. The rate can be average rate or instantaneous rate. Average rate is like over a span of time, like in first 1 hour or in first 10 minutes. Suppose in first 10 minutes or 10 between 5 to 10 minutes. This time is in minute.
Okay.
The concentration at the 5 minute it was 10 mole per liter as per the graph. At 10 minute it was 5 mole per liter as per the graph. Okay, so it has come down. So how do you measure the rate? Okay, this is going to be the average rate of reaction. Okay, average rate is measured over a long period, long time interval, and how you measure it, you divide the change in concentration by the time taken for that change. So you take the two concentration, take the difference, take the two time interval, take the difference that, okay. So here if I calculate it, so my concentration of the reactant, so final concentration, let's say the reaction is like this, A giving you products. This is the reaction. And this is the concentration of A measured at, this is 10 mole per liter. I have written capital M to represent mole per liter, and this is 5 mole per liter at 10 minutes. Okay, this point on the graph can tell me why y-axis will give me concentration of A. Concentration is written in a square bracket, and this is time in minutes. So I can make a table also. You can get a table also. So at 5 minutes, the concentration of A was 10 mole per liter. At 10 minutes, the concentration has become 5 mole per liter. So what is the rate of change of concentration? Can you help me calculating it?
10 minus 5.
Yeah, final concentration of A minus initial concentration of A divided by the T final minus T initial. Okay, that you know, that you may have done in 11th class also in kinematics. Okay, but there you were using the distance, and here we are using the concentration. And because A is a reactant, as you can see, it is written on the left hand side, its concentration is decreasing, and this term is going to come out to be negative. So rate always should be positive, so I put a negative sign. Or what you were telling, 10 minus 5, you can directly subtract a smaller number from larger number to get a positive rate. Okay. So now if I calculate, so, and this is represented by minus change in concentration of A. This is the short form. Delta represents change in concentration of A upon the change in time, and it is going to be 10 minus 5. I will, minus sign is just to make it positive. Okay, so if you are getting a negative sign, don't write negative, make it positive. That's the rule. So change is 5 mole per liter. Okay, and then how much time it happened? It happened in the interval of 5 minutes. So the rate of the reaction is going to be 1 mole per liter per minute is being consumed. Okay, this is the rate of reaction. So this is average rate. It is measured between these two time intervals. Okay, between 5 to 10 minutes. Got it? Any doubts in this?
No, sir.
Okay, good. So now the rate can be instantaneous also. Instantaneous is just like, suppose if you are traveling, and we can ask that what is the speed now. We will look at the speedometer in the car. That tells us what is the speed at which the car is traveling at that particular instant. So that is called instantaneous rate of reaction. Average rate is measured between two time intervals. Instantaneous rate is measured at a particular time, or a very time small, or you can say in a very small time interval it is measured. Got it? Just at a particular time. So suppose if you compare any reactant or a product, it can be, how can you tell me how it can be calculated? Instantaneous rate or instantaneous speed, you might have, if you remember in class 11.
dx by dt.
Yes, exactly, dx by dt. So same is the case here. So this can be calculated by d of change in concentration by dt. Exactly. Right? Minus sign is just to make it positive. Right?
Yeah.
The graph of the react, they will provide you table, and they will ask you that, okay, what is the rate between 5 to 10 minutes? What is the rate between 10 to 15 minutes? You need to know the concentration at that particular time interval. Okay, change in concentration and divide by the time interval, you will get average rate. And if you compare, if you calculate d change in concentration by dt, d concentration by dt, that will give you instantaneous rate. For reactant, the graph will be moving downwards. Okay, because the reactant are actually being consumed, so it's the graph of the concentration of reactant will be coming down. While if you look at the product, this is the reactant giving product. So graph, if you plot the concentration of product with respect to time, they are actually moving up. Okay, because products are being formed in the reaction. So here also you can see, you don't put a negative sign. So change in concentration is positive. Okay, and it will give you the slope. Dx by dt gives you the slope. Okay.
Okay.
Right. So this is about the basic idea of rate, and you can have instantaneous rate, you can have average rate. Mostly we deal with average rate, which is measured between the two time intervals. And let's say you are given with a reaction. Now we come down to a reaction, particular reaction. You will be given with a particular reactant in which A and B are reactants and capital C and capital D are products. And you balance this equation, these small a, small b, small c and small d are their coefficient of the balanced chemical equation. Okay. For example, you can have equation like N2 plus 3H2 giving you ammonia, 2NH3. Okay. So the coefficients are 1 is not written, okay, because it is obvious, 3 and 2. So reactants are being consumed. So you will say that you will calculate the rate of disappearance or consumption of reactants. That is the change in their concentration upon time interval. You will put a negative sign to make them positive. Similarly, B is also reactant. B also minus dV by dt. But product are being formed continuously. C and D are increasing, so you don't put a negative sign. For them also, you can calculate the change in concentration of C upon the time taken for that change. So dC by dt. Change in concentration of D, product D, divided by the time taken for that change. So for product, we are going to write rate of formation or rate of appearance, because they are forming. Right? So in this case, we can write minus delta N2 by delta T. What it represent? Can you tell me? This first.
Disappearance of N2.
Exactly. Rate of disappearance of N2. Rate of consumption of N2. Similarly, I can put this rate of consumption of H2. You will be given concentration and respective time interval. You can calculate them by taking the difference, dividing them. So rate of consumption of hydrogen, and there is a rate of formation of ammonia. Ammonia already you are going to get a positive because it is increasing, and this is the time. So now the next thing is, are they going to be equal?
Yeah, they have to be equal.
The rate of the reaction is related to all of them. But this is not the rate of the reaction. This is actually the rate of disappearance of nitrogen. This is rate of disappearance of hydrogen. This is rate of formation of ammonia. So they could be different or they could be same. That depends upon their stoichiometric coefficient of the balanced chemical equation. Okay. So think in just way, the coefficient here is 1. Okay. So suppose if 1 mole or X moles are reacted for N2, in the same time, 3x moles of hydrogen will also be reacted. Got the point?
Yeah.
So their rate obviously will be different because hydrogen is being consumed thrice as faster as the consumption of N2.
Yeah.
Got it?
Yeah.
Similarly, NH3 is being formed. Suppose 2 moles of ammonia will form or 2x moles, because as per the how I got 2, because the coefficient is telling me that 1 mole of N2 react with 3 mole of H2 to give you 2 mole of ammonia. So in the same time interval, you will be ending up with the 2x moles of ammonia. So by looking at these values, now one thing is sure, that the rate of consumption and the rate of reactants N2 and H2, they may not be same. Got it?
Yeah. Yeah.
And similarly, the rate of formation of product, that also may not be same. They may depend upon whether they are same or not. They may depend upon their respective coefficients, stoichiometric coefficient, whether they are same or not. So now the tension arises is, now I have a concern that which one should I consider to be the rate of overall reaction, because but they are different, but the reaction as a whole is one. That should I consider the rate of consumption of nitrogen as a rate of reaction, or should I consider the rate of consumption of hydrogen as a rate of reaction, overall reaction, or should I consider the rate of formation of ammonia to be the rate to represent the overall speed of the reaction? Got it? So now this is a trouble, and they all three are unequal. They are not same. We know that from the coefficient.
Yeah.
They are moving with different speeds. Hydrogen is being consumed thrice as fast as nitrogen. Ammonia is being formed twice as fast as nitrogen. So how to control them? How to make which one to consider? Now this is my concern. Okay. So now they are not equal. So now what I will do? I can't put this sign. It is going to be wrong. Got it? If I put it. But one thing I can make them equal. Something I need to do, because this was x, so this coefficient was 1, so they can divide it by 1, but needless to write because we don't write 1. Okay. Then the coefficient of hydrogen was 3, so hydrogen was being consumed thrice as fast. So if I want to make it, it was 3x. If I want to get it equal to the nitrogen, I will divide it by 3. Okay, so 3x I will divide by 3, x I will divide by 1. So now 3x divided by 3, it will also become x. Got it?
Yeah.
Similarly, for ammonia, it was forming twice as fast as N2. It was 2x. So in order to equate it, I will divide it by 2. Got it?
Yeah.
So now I can put this equal to sign. Okay, and now this will be called as the rate of overall reaction. Rate of reaction. So now we have seen how to connect the rate of disappearance of nitrogen, rate of disappearance of hydrogen, and rate of formation of ammonia, they were actually all were different from each other. How to make them equal? So in order to make them equal, the concept is very simple. Just divide them by their respective stoichiometric coefficient. Got it?
Yeah.
And they will become equal. And the whole expression will be equal to the rate of reaction.
Okay.
Okay. So this is very simple. So rate of overall reaction. This is the rate of overall reaction. It should come out to be same whether you calculate it from A, B, C, and D, but they were moving with different speeds. But when you divide them by their coefficient, respective coefficients of the balanced chemical equation, look here, we are dividing, they become equal. And that become the rate of the reaction. So you can now, this is a very important formula where you can calculate the rate of the reaction with any one of the reactant and product. With the rate of consumption of any one of the reactant or product, you can calculate the overall rate of the reaction. Right?
Yeah.
So let's do one question. This question is bit reverse manner. The equation is not given to me. Okay. But chemical equation of the is not given. But instead, it says that the reaction has A, B, C, and D are the reactant and products participating in the reaction. Now the question is asking me the reverse thing. It is asking me to frame the chemical equation. Getting my point? Reverse manner it is asked.
Yeah.
So what should be the chemical equation which can fulfill this criteria of rate of consumption and rate of formation?
Is it C?
So first we need to check this. D should be reactant or product?
React.
They both should be reactant. We can see the negative sign, okay, because the reactant are being consumed, so you put a negative sign. And A and C should be products, okay. And the coefficient of A is 4. Yes, coefficient of C is 2. Yeah, that's why I divided by 2. And they are product because they are being formed. There is a positive sign. On the other hand, B and D are being consumed. B and D are reactant. Yes, the coefficient of B is 1. The coefficient of D is 3. So absolutely correct. This should be the balanced chemical equation of the which can represent this above relationship. Got it? Okay.
Yeah.
So yes, correct. Absolutely. Now, suppose normally you are given with a chemical equation and you are asked to relate. So this already we have done. So rate of reaction is, this is, you can tell me quickly, very quickly.
Wait a minute. I think it's A.
N2, H2 and 2 NH3.
Yeah.
So minus N2, H2. H2 need to be divided by 3. Okay.
Yeah.
And N2 and H2 are reactant. So I put a negative sign. Negative, negative. Okay. Reactant need to put negative. Divided by 1, and no need to write 1 in the case of N2. 1 is already obvious. So that is this is divided by 3 and that is divided by 2. There is a plus sign. Okay, because ammonia is a product. So A is the right option. Got it?
Yeah.
Okay. Yes. So let's move to the next question. Actual reaction. Now get to the numerical. Okay, in the numerical we can see this is the actual equation of can you tell me what it is? Something related if you have carried out oxidation of I minus by permanganate ion. You might have done redox reactions in your school.
Yeah. Last.
Yeah, potassium permanganate and reducing agent was if you remember, oxalic acid. Okay, in
Okay.
titration you might have carried out the practicals.
Yeah.
This is also so this is also same, but in this case I have taken I minus.
Okay.
And this is 10 I minus, 10 iodide ion, 16 H plus. This is the balanced chemical equation. So now the question has given me the instantaneous rate of disappearance of permanganate. This is given to me, that is 4.56 into 10 to the power minus 3 mole per liter per second. So I'm provided with, let me write it in this way, minus of delta mn O4 minus by delta T. Okay. Rate of disappearance of MnO4 minus. That is equal to 4.56 into 10 to the power minus 3. The question is asking what is the rate of appearance of I2 in that time interval. The question is asking me rate of change of concentration of I2 in that particular time interval. Here you put negative sign for reactant, positive sign for product, but always remember that the numerical value should always be positive. Okay.
Okay.
So now they may not be equal because we know that here the coefficient is 2 and here the coefficient is 5. So how do we relate them first?
1 by 2 into the
equal to
is equal to 1 by 5 I2.
Yeah, 1 by 5 for I2. Exactly. Now it has become equal. When I divide them by their respective stoichiometric coefficient, they become equal. So now what is given to me? Delta MnO4 minus by delta T. I will put this value here. Okay. This value is here. Change of constant, not the minus half of. Okay. Minus half, we have put that minus half. What is given in the question? Rate of disappearance, delta MnO4 minus by delta T is given. So the question is asking me what is the rate of appearance of I2. So that we can calculate. Okay, just remove the negative sign. They are just symbolic. Okay, so 4.56 into 10 to the power minus 3 divided by 2 because it is half, and you multiply it by 5 if you cross multiply this. Okay, got it?
Yeah.
And negative actually we just write symbolic to tell whether it is a reactant or product, but answer should always remain positive. Numerical value all positive. Okay.
Okay.
So how much we are going to get? 2 into 2. 2.28 into 10 to the power minus 3. So it is going to be 10 and 11. 8 5 40. 5 to the 10 and 14. Okay, like this. 111.4 into 10 to the power. How much? Minus 3. Got it?
Yeah.
So I will, in order to write in scientific notation, I will shift the decimal here. So I will get it 1.1 into 10 to the power minus 2 as the final answer. I hope you understood.
Yeah, I understand.
Okay, so simple. Okay, but if somebody asks me what is the rate of the reaction, then what you are going to do? Overall reaction.
I have to add also.
Yeah. Rate of reaction. You can remember this was the expression. Okay. So I will write the complete expression also. and so on. Okay.
Okay.
So rate of reaction, when we divide them by stoichiometric coefficient, we get the rate of reaction. So I will put this value and divide it by 2. So that will be the rate of the reaction. So rate of the reaction is 2.28 after dividing by, no need to multiply it by 5
Okay.
into 10 to the power minus 3.
3.
That will be the rate of the reaction.
Okay.
So I hope you understood it.
Yeah, I understand.
Okay. So let's move on to the next question. This is also just try, you can try it little bit, and I hope you will be able to do it. So this is actually oxidation of NH3 in the presence of oxygen, and that gives you nitrous oxide and water. So rate of formation of NO in some time interval is 3.6 into 10 to the power minus 3.
Okay.
The question is asking rate of disappearance of ammonia and rate of formation of water in that particular time interval only we can tell. Okay.
Okay.
So what they should. So just write and tell me
Yeah.
whether we can get the answer or not.
Yeah, I'll try.
I can give you a hint that the coefficient of ammonia and NO are same.
Yeah, I got that.
Yeah.
The rate of disappearance of ammonia is 3.6 into 10 raised to minus 3.
Yes, exactly.
And then the formation of water is it 5.4 into 10 raised to minus 3?
Yes, exactly. Yes. So you can sometimes the without solving numerical, but in CBSE you have to write. Okay. But if you are pursuing mains, advanced, and or NEET, okay. So what you are interested in? Are you pursuing any mains or advanced also or NEET?
Yeah, I might go for NEET.
Yeah, NEET. So there, because the time is less, so you can just look at the coefficients. So both the coefficients are same. Okay.
Okay.
So 1
Yeah.
by 4 of NO, 1 by 4. So they will move with the same speed.
Yeah.
So NO and ammonia, so this no need to calculate this. Okay. So directly I got rate of
Yeah.
consumption of ammonia same as that of the rate of formation of NO. And what about the rate of formation of water? That I need to calculate by taking this 1/4 of NO by dt dNO by dt equal to 1/6 of dH2 by dt. Okay, so you got the right answer. Good. So let's move ahead. Yeah. So this is a simple question. I have taken questions from NEET and mains both. So look, basic questions of both. So you can try such questions. You will find NEET also with the same data. Some change data you will find. Okay.
Yeah.
This has not given us directly the change in concentration. We need to calculate it.
Yeah.
So the moles of N2O5 got reduced from 3 to 2.75. The changes of 0.25. In how much time? 30 minutes. So this is equal to minus d N2O5 by dt. Okay, this minus is just symbolic to mention that we are getting, this is a reactant. Okay. And what they are asking the rate of formation of atoms.
Yeah.
So if I want to make them equal, I should write it in this way. This numerical value is only for this one. Okay. Got it?
Yeah.
So dNO2 by dt will be equal to 4 times dN2 by dt. So it will be equal to twice of minus N2O5 by dt. So it will be twice minus dN2 by dt is the one which we have written above. This is twice 0.25 by 30. Okay. So 0.25 is 1 by 4. So I will make it simple. I will write 0.25 as 1 by 4. Okay, 2 by 4. And 1 by 30. So it is equal to 1 by 60 mole per liter. 1 by 6 is how much?
1 by
1 by 6 is 6 point is point 666. Okay. Hence, because it is 1 by 60, not 1 by 6, so it is going to be this much. Got it?
Yeah.
Any confusion in this?
Yeah.
So this is going to be the answer. Normally, there is one confusion which I have observed among students is that this rate, they get confused whether it is half of the value which is given is the value of half multiplied by this or this. They get confused in this one. But you need to concentrate that the question is giving me the change of concentration of N2O5. So the value they are providing me is not minus half of the N2O5 dt, but they are actually giving me the rate of change of concentration of N2O5 by dt. Okay. This they are providing. I need to divide it by 2. I need to multiply it by minus half to make it equal to the rate of the reaction. Got the point?
Yeah.
So yeah, so let's so this is a lot of questions you will see in NEET, same pattern of questions but with different data you can observe. And one more thing, be very careful about the units of time.
Yeah.
Keep an eye on the units of time, because sometimes what happen is they give the two same values, because we are so busy with the calculation that we forget the units. Suppose if I get this as answer and one option will say mole per liter per minute, okay, but the first option what they are going to do, they are going to give you like this. Normally we are busy with the calculation, we think that, oh, we got the answer, this was the answer, without looking at the unit, so this will become wrong. Okay, so keep an eye on the units of time, because they will give you two values, 0.1666 mole per liter per minute, okay, with the same magnitude and a different unit of time. So keep and so in question you need to look at the question first. So time, whatever they are given, whatever units, 30 minutes they are given, so you need to choose the final calculation in minutes only. Got it?
Okay.
Be careful, because these are some common mistakes which students do in their examinations.
Okay.
Next is, what are the factors? So these are the basic thing where you will be provided with rates and all. Okay. Now the next thing is, what are the factors which affect the rate of reaction? How the speed of reaction can change? The thing is, most common is the nature of reactant and products. Whether the reactants are more reactive or less reactive, okay, that can, this is actually qualitatively I'm telling. But if you get into the numerical, the concentration of reactant, this is the most important. So can you tell me roughly that how concentration affect the rate?
Pardon?
How can you tell me how the concentration of reactants can affect the rate of the reaction?
I think last year we learned according to Le Chatelier's principle. When the concentration of the reactants increase, then the reaction will move in the forward direction in order to.
Exactly, and the rate is going to be more.
Yeah.
Because you have more reactant and more collisions are going to happen, and the chances of reaction will increase.
Yeah.
Okay, so more concentration, more rate. So concentration is a key factor for change in rate of a given reaction. Rate is proportional to concentration. Okay, roughly if I say. For gases, I can replace the concentration with pressure also. Understood?
Yeah.
Because concentration, if I take more pressure of gases, for gaseous reactant mean more pressure. More concentration, pressure will make them more concentrated. Okay. So the first most important thing is rate of the reaction depend upon the concentration or the pressure of reactants, right?
Yeah.
Do catalyst affect the rate of the reaction?
I don't think they affect. They lower the activation energy.
Exactly. They lower the activation energy, but they don't change the position of the equilibrium, but the equilibrium is attained more quickly.
Yeah.
That's what we tell. So now suppose if the reaction is happening in this way, this is the energy profile of the reaction. This is the energy which is required for the reaction to happen, reactants, and these are the products. Okay, this is the energy profile.
Yeah.
Right, products. So without the catalyst, this is the progress of the reaction, and this is the energy. Suppose if you take the catalyst, though the percentage of reactant and product formed will remain same, the equilibrium constant will remain same. This is with the catalyst. But as you told very correctly, that catalyst is going to provide a low activation energy pathway.
Yeah.
Some indirect route will be provided by the catalyst. Catalyst change the reaction and let it proceed to lower energy path. Means more number of molecules which were earlier not able to react because of the higher energy requirement. Now they will be able to react and form the products. Got it?
Yeah. Yeah.
So the speed of the reaction is going to change. It is going to become faster. Right? Catalysts affect the rate of the reactions. They make it faster. But they do not affect the percentage of the products, the concentration of the product, final concentration. Catalysts do not affect the equilibrium constant. Overall, suppose if you are getting 10 moles of product without catalyst, finally also you are going to get the 10 moles of product with the catalyst, but in less amount of time.
Yeah.
Catalyst also do not affect the heat of reaction that you may have studied in chemical equilibrium. Or okay, the heat of the reaction is whatever the difference between the energy of the reactant products. That is going to increase. So as far as kinetics is concerned, we can say that the catalyst increase the rate of the reaction and they provide the reaction with a lower energy path. Okay. What about temperature?
Temperature plays a role on the rate of chemical reactions.
How it affects the rate
But
of...
I don't really remember how.
Okay. So what happens is, suppose you are increasing the temperature. What you are increasing with the temperature?
Heat.
Yeah, we are increasing the heat. We are increasing the energy of the molecules. Got it?
Yeah.
The molecules, suppose if they are at lower temperature, they will move very slowly. Right?
Yeah.
They keep moving and colliding with each other. And that's why they react. As per the collision theory. They react because they collide, they break their bonds and form new bonds to which are thus they lead to the formation of products. Okay. So as you are increasing the temperature, you are giving more energy, you are giving the heat, exactly what you said, means you are giving more energy to the reactant. They are moving with more speeds, and because they are having now possessing more energy, they are now more capable of forming the products. Got the point?
Yeah.
So as you increase the temperature, the reactant molecule possess more energy, and they can easily overcome this energy barrier, and they can form more easily, they can form products. Also, there is increase in collisions, more energy. So overall, I would like to summarize that the speed of formation of product increases, speed of reaction increases with the increase in temperature. Got it?
Yes,
This,
I got it.
yeah, this you can in real life example, suppose a piece of coal is there that will not burn normally at room temperature. It will not burn because it is not heated up properly. But as you heat it to higher and higher temperature, it can burn easily because you are providing it more energy, so more coal particles can react. Next is, so with temperature increases, rate of reaction increases. You take it at low temperature, speed slows down. Now you have surface area of the reactant. Surface area of the reactant, it is a matter of concern only in the case of solids. Because gases and liquid, you don't talk about surface area, they completely mix into each other.
Yeah.
So if the reaction is involving any solid, there area of the solid can increase the rate of the reaction. If you take the solid in powdered form, it can the more surface area, it will be more exposed. The reaction can happen at more places on the solid. So that's why it is told that whenever you are taking a catalyst and catalytic hydrogenation reaction, we take it in the powdered form, right? So increase in surface area will increase the speed of the chemical reaction. Exposure to radiation, yeah, that also may affect the speed of the reaction, but these 3 points are not applicable in all type of reaction. This is for only for solids.